Hello and welcome to Beamer Folk.
I thought I would share with you some more of my lockdown electronic doodling, and this is with a board which I've actually had for about 4 or 5 years. It's quite a common, inexpensive little board that many people have purchased off a well-known auction site, and it's an LED&KEY board, and I've played with this a few times over those years. A lot has been done with this board by other people and said it's got the main chip on here, the decoding chip that drives the LED display, the LEDs and switches, is a TM1638, and I'll leave the data sheet for that in the description below. And it's a digital voltmeter, well in fact 6 digital voltmeters, and I've separated out, you've got here a 4-digit left hand display and you've got a 4-digit right hand display. I've managed to achieve, with the use of an Arduino Nano, a 6-way digital voltmeter. It's only 2.5 digits, and I'll show you it in operation in a moment. And I've been quite pleased with it. It does represent a start. It's not a finished idea, and I can think of at least one application for it. There might be others, but I can't actually think of them. But anyway, I'll now introduce you to the rest. So here we are, all wired up. I'll just plug it into a USB. The board itself I think is ideally operating at 3.3 volts, but it works quite nicely on 5 volts, and I've not experienced a problem in doing that. Now let me just plug the supply into a USB bank, and you can see what's going on here. We've got here a breadboard which marshals the wires, and I've got a ladder network from 5 volts, I think it's 7 1K resistors. The circuit diagram of that will be included. So you've got that, you've got a small capacitor there across the supply just to smooth out any noise. A DVM is a bit sensitive to noise on the supply line, and I thought it wise to do so, and it does help a little bit as far as I can see. Now to the board itself, the LED&KEY board, we've got here a sequential pair going in 3 positions. Number 1 position pair, number 2 position pair, number 3 position pair, and that's indicating the pair of digital voltmeters which are actually being displayed. The digital voltmeters go on the Arduino Nano from A0 through to A5. So the first LED is A0 going through to here, which is A5. The first pair of DVMs are presented here. So you've got the left DVM here, the right DVM, and then you've got the next pair, which is the second in the sequence, which is the left DVM and the right DVM for that sequence, and then finally the third sequence, which is the 5th and 6th digital voltmeter, left and right. You can see that the display is only 2.5 digits. It naturally goes from 0 to 5 volts. So on the most significant digit here, you'll only get a reading of 4.99 as a maximum from 0. The switches on the board, so far my experimenting, are not in use. I can see a possible use for them with this, but at the moment that's for the next development of it really. So what have we got? So we've got the power supply connected to the ladder network. The ladder network is reading from a very low voltage to a high voltage, and the ladder network itself, let me calculate it. So going through the calculation, it should read from the lowest on this ladder network 0.71, the next one 1.42, the next one 2.41, the next one 2.85, the next one 3.57, the next one 4.28. That's the highest level, and I'm pretty sure it will actually get to 5 volts, although I'm not quite sure the linearity is so close to the supply. But you can see how that works. Okay, what use could you put this to? I struggled a bit, if I'm honest, but the one thing I could that I thought of is a test bed for a circuit board. So it would be a bed of nails, and around the circuit you would want perhaps voltages measured at 6 points around the circuit in different locations. The input impedance to this digital voltmeter is extraordinarily high, so there wouldn't be a problem with loading. This could be part of a test fixture. That's the thing I thought of, and perhaps you can suggest something else. Maybe you can think of something which I haven't, and if you'd like to leave those in the comment, I'll explore them. Okay, so what is its weakness? There is a very slight error, and we've alluded to it just now, and that is the least significant digit here and here can't quite make up its mind whether it is one digit or another. Well, of course, if there is let's say a 0.5 as the next digit to the least digit, as it were, obviously that would place a dilemma in the digital voltmeter logic as to whether it is going to be the same digit or the next digit up. So there's a dilemma there, and obviously anything less than let's say 0.5 would fall to, let's say, the lower digit, and anything greater than the 0.5 would fall to the upper digit. So there is an error there somewhere. The reason why 2.5 digits I chose is simply because the resolution of the A to D converter within the Nano is 0 to 1023. That is 1024 discrete steps, and each step I think was 40 millivolts. So as you're looking at here, 100 millivolts there and 10 millivolts there, you can see that you couldn't improve upon the resolution given the limitation of a 10-bit A to D. So the best I could do with this was 2.5 digits. You could make the digits scaling up in the software to possibly any number you like, but the resolution would still stay the same. But if you could also do on the input, you could do a resistive scaling so that you could have, say, for example, 0 to 10 volts. You could make the 0 to 5 volts here via software to, again, 0 to 10 volts. But again, you wouldn't improve upon the resolution. So there's not much point in doing it there. But you certainly could do it resistively. As far as this little project idea goes, the next step I'd probably make is see if I can employ these switches so that if you push one of these switches, one of 6 switches, this display will fix on that particular digit. Or in fact it would be, let's say, one of 3 of the push button switches, where the first button would be holding on the first pair, the next one the second pair, and the third one the last pair. And that is the next thing I will try and implement, and I'll carry on and see if I can think of anything else I can do with this. I thought I'd finally demonstrate the error in this DVM, which you might be able to help me with. So what I do is I remove the 5-volt supply to the resistive ladder network. So all the high impedance inputs to the A0 to A5 is clamped to 0 via the ladder's 1K resistors. So there, as it's a low impedance, we shouldn't really get any residual voltage displaying. So let me do that. Let me just take the supply to the ladder network off and put it there. Now all the DVMs should now be reading 0 volts, and as you can see there's a little bit of lifting above 0 on the last significant digit on all DVMs, and it can go up to 2 and 3, as you can see there. I've tried, and it did help. I tried putting a capacitor across, as you can see, as I showed you before. I put a capacitor across the supply, and that helped a bit. But there's something causing the DVM logic to kick in those 1, 2, 3 digits of least significance up from 0, which is where it should be. I've put a bit of effort into trying to eliminate this, and I've got it down to the A to D conversion in the software. I'll explain that in a minute.
We have before us my Arduino sketch for the LED&KEY DVM times 6 digital voltmeter. I would like to go into this in fine detail. I'll probably run through it quite quickly. Because it's quite involved, it'll probably need a separate video to do this more thoroughly. So it'll be a kind of fly through on this. It is included, there is a link for it in the description below. Before I get into that, I was just going to say I've made improvement to the last significant digit offset voltage, which was flickering around a bit. It looks as though the breadboard and links, these rather inexpensive wires, links and pins, is developing a small millivoltage drop across them. So I've improved the issue by connecting the other ground on the Arduino Nano, joining it to the ground on the breadboard. This seems to have improved. It's not totally eliminated, but it's now flickering between 0 and 1 digit. And I think if you actually assembled this onto a proper board, you'd probably eliminate it completely. It looks as though that's a solution. But if anybody else can offer any advice, please leave it in the comments. To the sketch itself, you have here the segment mapping to begin with, and that's a little pictorial diagram. You've got the line 789 on the Arduino for the strobe data and clock. You have here a dimension that sets up this column here. Further down, all this of course is setting up the variables. You have here the refresh period set to 400 milliseconds. That is literally the period of time that the DVMs get refreshed. Further down here you have the state machine starting point, which is sequencer 0. And further down you have here a variable which sets 10 seconds. So it holds the pair of values for this period. And of course 10,000 here represents 10 seconds. If you wanted it longer, you could put 20,000 here. If you wanted it shorter, you could put 5,000 down here. Moving on down to the setup, you have Arduino Nano pins for 7, 8, 9. I think it was, let me go back up. 7, 8, and 9 are set up as outputs for strobe data and clock. The next line sets the brilliance on the 3-digit display here. You can make it brighter, you can make it dimmer, whatever you like, by changing this number here, this hex number there. The next section is resetting and clearing. That basically clears the display and presents zeros. Okay, that's the setup complete. Now the loop. The loop is really, as I say, I'm going to do this quickly because it's a bit complicated, but it's a loop within a loop. And in principle, when you look at the beginning of this, you have two display calls to subroutines. One's for the 3-digit left-hand display, and the other one is for the right-hand display. The data for those two subroutines are, let me show you the actual subroutine display 3 digits, and then we get a better grip. Here we are. This is the left-hand one, and you can see it's doing maths here using the remainder symbol here. It's doing maths here to derive the actual 3-digit display. It's probably already 2.5 digits, isn't it? Doesn't go more than 5. That's for the left-hand one, and that is for the right-hand one. Going back to the beginning here of the loop, you can see that's being called here and here. Well, it derives its information from the sequencer, and that starts off at case 0, which is defined as a start point, do you remember, above, which is 0. And in here, in principle, this is repeated for the 3 sequences of the all 6 digital voltmeters. So there's repetition going on here. The first thing is to describe, which is what's going on here. It's turning on the 2 LEDs on the far left-hand side, which is the first pair of the sequence of 3, and that is C1 and C3. You'll notice that it's not C1 and C2. It seems to be kind of interleaved. So that turns on the first pair of LEDs. The associated analog inputs, nano analog inputs, are A0 and A1, and they are derived through the read function. So a read function is called, that A1 is read and stored as DEC left. Another input is read, which is A1, and that again is stored into DEC right. Then, of course, it moves on to turning off those pair of LEDs, eventually coming out at sequence 1, which is case 1 here. Then the next pair of LEDs are turned on, which is the second in the sequential function, and that is C5, C7. Again, C6 is missing. And those associated analog readings, A2 and A3, which is the analog inputs of the Arduino Nano. And those functions again put in left, put in right, and then it eventually moves on to turning off that pair of LEDs, and then moving on to case 2, which is the final pair of analog inputs, and it turns on naturally the C9 LED and CB LED for the display, and their associated analog inputs is A4 and A5. That goes into A4 left, A5 goes into right. Then, of course, the LEDs are turned off, and after that, after a period of time, the sequence then returns back to the beginning. But I just go back to just look at the beginning of that loop again, which is here, And so just reminding us that that information then goes on to the subroutines display 3 digits left and right. Now just have a quick look through the subroutines before we finish. We've got the read function here. It's averaged out over, I take 4 readings and effectively adding those together and dividing them by 4 produces a smoothed out average. That's divided by a special number here, and that converts the, what is it? It's 1024 discrete steps for the analog to digital converter in the Arduino Nano, and that has to be converted to the 3.5 digits, and there's a little bit of maths going on here to derive that. We've gone through the next, that was the read function call. This is the display 3-digit left-hand side function call. That's where the maths goes on for the left, as we described earlier. That's the maths that goes on for the right. The send command function generates a word, and any information that goes to the, what is it, the TM36 chip, any directives that go in have to be shot out via the send command. To control the LEDs, this subroutine .led does that, and then finally you've got the digit do call subroutine. It does the same for the 7-segment digits, and it's a very similar structure to the individual LEDs. Well, I've skipped through there as quick as possible. I'm sure it's not my explanation is not totally accurate. Some of this I constructed about 4 years ago, so my memory for it has got a bit shaky, but I've done my best here, and perhaps I need to do a more thorough, in-depth explanation, and that could be done in a separate video. This is Beamer signing out for now.